Hello, chemistry students. We're still working on Big Idea 2, and I wanted to go through some different just kind of examples that are the sorts of things you'll probably see on the exam. So you'll probably get something like this, a chart like this, and you may be asked about bond strengths, right? You might be asked about why one particular bond is stronger than another or whatnot. So let's do some of this and kind of do some interpretation on this. So let's look at this chart over here, and let's just compare a couple of examples. Let's compare nitrogen and oxygen. So if you're looking at N2 and O2, the question might be asked, which one has a stronger bond? And so you're going to have to analyze the two. Well, we have nitrogen right here. If we look right here at nitrogen, it is a 145 as far as bond length goes, right? So its length is 145. You look at oxygen, its length is 148. So what does that tell you? Well, that tells you that oxygen has a more distance in between the two atoms. So oxygen is somewhat of a further atom away from the other atom. And so one thing we learn is that the strength of a bond has to do with how far these things are away from each other. And the reason why oxygen and nitrogen are different is because of this extra bond in nitrogen. So nitrogen is a triple bond, right? Whereas oxygen is a double bond. And that makes nitrogen closer. Oh, did I draw oxygens? Well, I did not mean to do that. That makes nitrogen closer to the other nitrogen, you see. And so what about energies? If we look at energies, then that also goes to match. So the bond energy for nitrogen is 170. So it's going to take more energy to break that bond than it will the oxygen bond, which is 145. Okay, and that's all because of this triple bond. This triple bond is going to be pulling these a little bit closer to each other. And also another thing that factors in is that nitrogen is slightly smaller when you look at the periodic table, they're right next to each other. So the size difference isn't very big. But when you do analyze size difference, for example, let's pick on hydrogen bonded to another hydrogen and a chlorine bonded to another chlorine. Well, in this case, they're both single bonds. But when we look at bond length for hydrogen, we have 74. So this is really, really, really close to the other one. And for chlorine, we're looking at 199. So, more than double the distance away. And so what does this tell us? Well, it essentially tells us, since there's only a single bond, that the thing that pushes these further away from each other is the sheer size of the chlorine atom compared to the size of the hydrogen atom, which is much smaller. So because these are so much further away, it's easier to break these bonds than it is these bonds. And if we look at the bond energies right there, we got a 436 versus a 243 for chlorine, right? So here's the energy, and this is the length right here. All right, so the two things, when you're talking about bond strength and bond length, two things you sort of want to look for right off the bat is the size of the atom, okay? Because the smaller they are, the closer they'll be together, right? And the closer they are together, the stronger the bond is going to be, okay? And the second thing you want to look for is the number of bonds, because if I have 3 bonds pulling together versus 1 or versus 2, it's going to bring me closer together. And the closer I'm pulled together, the harder it is to break me apart. And so therefore, that's going to be a stronger bond. So those are kind of two things you're looking for. Another thing that you might be asked to sort of identify would be, what's the bond strength, or maybe the question would go something like this: why NaCl boils at 801 degrees Celsius, right? Magnesium oxide, on the other hand, boils at 2852 degrees Celsius. So enormous difference in boiling point. And so boiling point is going to be something that's going to cause these things to come out of their ionic lattice. Both of these are ionic bonds, right? And so they're different than these ones up here that we talked about. So these ones up here, it's all about bonds. These are covalent. But when you're dealing with ionics, what we have with ionics is we have a crystal lattice, right? And so these crystal lattices form in between these ionic bonds where they connect to each other and they make a three-dimensional shape, okay? So something like that, okay? So that's my best three-dimensional. That's pretty bad. Okay. So anyways, they have these crystal lattices. Now, what is it that gives these crystal lattices their strength? So to break apart this crystal lattice, or boiling point anyhow, you could say, would be, is so much more difficult with sodium. Actually, this is not boiling point, this is melting point. I don't know why I said boiling point. Probably because I said boiling point up here, or no, I didn't, but anyways, forgive me. Melting point. So this is the actual temperature it takes to take the solid sodium and get it to go into liquid form. And so that's when we're breaking the ionic crystal and turning it into liquid. Okay. So melting point, and these are the melting points of these two chemicals. Now, when you look at sizes, we talked about sizes up here. The size of sodium and chlorine is really similar to the size of magnesium and oxygen. That's not what it is. These are very similar sized things. But what we're looking at when we're talking about the melting points of ionics and the strength of ionic bonds is charges. So if you look at sodium, it's going to be a +1 and a -1. That's what's holding this together, is +1, -1. That's what's here. And in magnesium oxide, it's +2, -2. So the size of these charges between ionics, that's going to make the big difference. And that's going to change the melting points. If you're asked, why does magnesium oxide melt at 2,800 degrees, whereas sodium 801? Well, the difference is that this has more charges holding these things together. So, and just a quick, if you're really going to get technical, and actually probably if they ask a sort of question like this on the AP exam, you're probably going to want to mention Coulombs Law, right? So Coulombs Law says that it's comparing Q1, Q2 divided by the radius squared. So Coulombs Law is comparing ionic bonds and the electrostatic forces in between them. And so magnesium oxide is way more highly charged. It's got the +2 and -2. So the Q1 and Q2 here are going to be +2 and -2, right? And I told you the radius between them is about the same. So it's going to give you double the amount at least for Coulombs Law. So Coulombs Law is going to give you sort of a value for those electrostatic charges. And so, you might want to say, according to Coulomb's law, the charges, or the higher the charges, the higher the electrostatic force, therefore the higher the melting point. You could say something like that. But you do want to make sure to bring this Coulomb's law into it when discussing the difference in melting points in ionic solids.